Dr. Raghu Prakash will be joining.
Sorry, professor has held up with some other work.
Okay.
I'll start the webinar, sir. I'll start and can.
Okay.
You can just give it another couple of minutes, Dr. Vishnuvardan.
Yes, sir. Yes, sir. I think Sundar sir has joined.
Yeah, good evening, and it's a pleasure to hear Dr. Mathew's voice. It's been a long time.
Yes, Dr. Sundar, same with me too. I think, in fact, for me, I was thinking a bit nostalgic because I still recall meeting you and Dr. Raghu Prakash many decades ago in NIL and subsequently in Kalpakkam, and every time for the Kripati
Right.
conference series.
Yes.
So those memories, those meetings are etched in memory. So
I think we missed you at the Icons meeting in August. I was there.
Yeah, but see, I retired from IGCAR 9 years ago, so I am a kind of out of the loop now. So I'm now.
Well, people like you never get out of the loop, when it comes to the subject. So.
Yeah, so I ended another loop. So I relocated to Kerala, my home state, and then I joined an engineer. I was just sharing with
Okay.
Dr. Vikram. Yeah, I joined an engineering college here, where I do teaching as well as guide faculty and PhD scholars for their research activities. And of course, I have quite a bunch of administrative responsibilities also. So that keeps me busy, but it's a different loop. Because
is
in my
Dr.
college,
Sashikala also part of the loop?
At least not on the same loop, as far as I know. And in this college, there is no metallurgical engineering course. So, to be honest with you, after I left IGCAR, I am not doing any active research. So when Dr. Raghu Prakash contacted me, I was wondering whether I should use the old wine in the old bottle or because I have not done new research since I left there, because in this college, no metallurgical course. In fact, in the whole of Kerala, in NIT Calicut, there is a PG program. And one engineering college, private sector, there is a UG program in metallurgical engineering, and not in my college. So,
But seminars like this, whatever we've had thus far, they have not been a platform to come and present something absolutely new. It's for us to get a good feel for related subjects in a way that can be understood by a wider community. So what you're going to talk about, I'm sure will be both interesting as well as valuable, both for the more experienced people who are listening in, and particularly so for the younger people who can get a feel for what's happening in different related areas to structural integrity. So it's really great that you're able to come and present your work.
Thank you, Dr. Sundar, for the kind words. I agree with you because, I was fortunate to have done quite a bit of work, a few of it with pioneers in this field. And there are a lot of things that remain to be done in this area. So to that extent, I thought it may be a good opportunity to share whatever I have understood and whatever probably the opportunities that exist in this field with this special community. That's why I agree. And definitely, it is good now because I have been able to at least meet some of my old friends virtually.
Right. We have to thank Raghu.
Yeah. I think Dr. Varaprasad Reddy is there, right? Because now I'm in the presentation mode, I can't see the names.
Yeah, and Vikram, they've been able to really bring in a lot of involvement of specialists in different related areas. So InSIS is doing some great work in this regard.
Yeah, it's a very significant area, no? And important.
So warm greetings, sir, Dr. Mathew, sir. After a long time, I'm seeing you.
On my screen, I can't see the name or face because I'm in the presentation mode unless I.
Yes, yes. Yeah, when the meeting started, I saw you.
You are Dr. Varaprasad Reddy?
Yes, sir. Yes, sir. Warm greetings.
Yeah. Okay. I'm able to kind of recognize your voice.
Thank you, sir.
So how are you doing?
Yes, sir. I'm fine, sir. In fact, I'm very thankful to you because creep section is very intact. I mean, the regards goes to mainly you only. The way you have established.
I congratulate you for keeping it intact.
No, sir. The facilities what you have established for the younger generation like us, they're still highly rigid and generating very repeatable data. In fact, many of the missions. So
That's
my heart.
Perhaps we should get started, Dr. Vishnuvardhan.
So can I start?
Dr. Vishnuvardhan. Can you hear me?
Yeah, yes, sir. Good evening, everyone. Professor Vikram Jairam, Dr. Sundar, Professor Mathew, other InSIS Executive Council members. Welcome to this webinar, which is organized by Indian Structural Integrity Society, InSIS, and Center for Structural Integrity of Safety Critical Systems of IIT Madras. And Professor Raghu Prakash could not join, so kind of starting this webinar. Today's webinar is on non-destructive assessment of structural integrity of components using micromechanical tests by Dr. Mathew. A brief intro of Dr. Mathew. He is currently a professor in the Department of Mechanical Engineering, the Research Dean, and the Associate Provost at Saintgits College of Engineering in Kottayam, Kerala. Prior to joining the Saintgits, he worked as a scientist at the Indira Gandhi Center for Atomic Research, Kalpakkam. And during his research career at IGCAR, spanning over 35 years, he made several contributions towards the development of fast breeder and fusion reactor technologies in India. His research work led to the indigenous development of many advanced materials for critical applications in nuclear reactors. Dr. Mathew is a graduate in metallurgical engineering, postgraduate in physics, postgraduate in business administration, and a doctorate in physics metallurgy interdisciplinary. He has published over 200 research papers in national and international journals, presented more than 100 research papers in national and international conferences, and published several books and book chapters. And he is currently an editor, key reader, reviewer of 17 international journals. He has been ranked among the top 2% scientists in the world by Stanford University, USA, successfully in the years 2020, 2021, 2022, and 2023. He was awarded Asia's Outstanding Researcher Award in the year 2023 for his outstanding contributions in the field of nuclear technology and nuclear energy. He is a program evaluator of the Accreditation Board for Engineering and Technology, ABET, USA. He is a fellow of the Indian Institute of Metals, fellow of the Institution of Engineers, India, fellow of the Indian Institute of Welding, member of the Minerals, Metals and Materials Society, USA, member of Global Engineering Deans Council, USA, and life member of several professional bodies in India. He has received research fellowships from several countries, including Japan, South Korea, Germany, and USA, where he carried out research work at major nuclear research centers and universities. Over to you, Professor. And I request attendees to post your questions in the chat box, and those questions will be taken up after the presentation. Over to you, sir.
Thank you. Thank you, Dr. Vishnuvardhan. And good evening to everybody. Professor Vikram Jairam, Dr. Sundar, Dr. Varaprasad Reddy, members of the Executive Council, and other participants. In fact, when I received an email sometime in October from Dr. Raghu Prakash and Dr. Vikram Jairam about inviting me to give this talk, I was pleasantly surprised because it was after a long time, and having left IGCAR, retired from IGCAR for in 2014. So I have not done very active research in this area. So I was wondering whether I should accept it or not. As we were discussing earlier, I thought that, okay, it may be a good opportunity to share my old knowledge and past experience and also highlight the potential for future research in this area. So that is how where we are now. Of course, the initial date was postponed once, and then today on this 20th of January, we are having this presentation. So I'm indeed very thankful to both Dr. Raghu Prakash and Professor Vikram Jairam for inviting me. And as I mentioned, what I'm going to present will be the work that I carried out when I was at IGCAR and also with some of the pioneers in this field in other countries. So as the title goes, it's all about structural integrity of components, about the mechanical properties from micromechanical tests, as I call it. And you will understand that it's a kind of non-destructive assessment of the mechanical properties. When we say non-destructive assessment, we think of other things, but in this case, it's about mechanical properties. So we are all familiar with mechanical properties of materials like hardness, tensile, compression, fatigue, creep, impact, and fracture. To evaluate the properties of materials, we do standard tests, mostly as per ASTM standards. And this requires a lot of specimens. We need to repeat the test at least 3 times to have a good number. And from one specimen, you can get only one data point or one property. So we need to have a lot of material. We need to carry out a lot of tests in order to have a reasonable database. But here I am going to discuss with you and share my knowledge on 3 innovative tests. The special feature of this test is that these tests are material non-intensive. That means you don't need much material to do these tests. Or with a limited amount of material, you can generate a large amount of data. So once you have only limited amount of material and from one sample, perhaps you can generate more data, as you will see going forward. That would mean that a lot of sample preparation work can be avoided. Variations, sample to sample variation in the data can be avoided. So there are many advantages for these innovative tests. And which are these tests that I'm going to talk of? These are about ball indentation, from which you can evaluate the tensile properties, the fracture properties, and the hardness of the material. The other 2 are small punch creep, impression creep. As the names go, we know that's all about creep properties. So what you see on the right side is a small impressions, ball indentation test impressions made on a small sample size. You can see that each of these impression gives you one data point with respect to the tensile or fracture properties of the material. So from a small piece, you can do a large number of tests. So this becomes useful in the case of structural integrity evaluation, which means you can scoop a small portion of the material without damaging without compromising the integrity of the component. You can scoop out a small piece, and that can be used for these kinds of tests. And of course, the scooped portion, you can do some weld overlay and repair it. And the results that I'm going to present, as I mentioned, at IGCAR, there exists a state-of-the-art laboratory for carrying out evaluation of materials using these innovative methods of both ball indentation, impression creep, and small punch creep. And I was fortunate to have been able to work with some of the pioneers in this field at North Carolina State University on the ball indentation. at Kagoshima University on the small punch creep, and also take inspiration from pioneers like JCM Lee in impression creep, and late Professor D.H. Shastri from IAC also on impression creep. So what are the advantages of this innovative tests? As I said, this is material non-intensive. You need only small amount of data. See, in a conventional creep or tensile or fatigue test, you need a lot of data. You take a really a small piece of plate itself and cut it into small mini strips, and then blocks or blanks, and then machine them into samples. Each may be 100 mm long or 10 mm diameter, etc., etc. So that there's a really material intensive testing. On the other hand, these tests are material non-intensive, so you need really a small amount of material, and that is the big positive about these tests. So large amount of data from one sample. And these tests, except in one case, they will leave only a small impression in the material. And that is why I call it non-destructive. It will leave only a small impression and maybe some compressive stress. So that qualifies it as a kind of non-destructive test. Therefore, it becomes suitable for structural integrity assessment, assessing the remaining life of materials, and you can use it for materials development. Suppose you are developing a new alloy where you will be making a large number of laboratory heats with minor variations in compositions, and you need to do a rapid screening of this. It comes very handy because you can these tests are short. You can do this test very quickly, so a large number of these heats can be characterized for screening purpose. And another big advantage of these mechanisms or methods is that you can characterize the creep properties of different microstructural zones of weld joints. We all know that a weld joint, ultimately the integrity of a weld is decided by the properties of either the weld metal or the base metal or the heat affected zone, and weld is always considered to be a weak link. So it is difficult to determine the properties of each of these zones. Either you make you make a big weld pad and then prepare weld metal samples, or from the parent material you prepare base metal samples. But it is very difficult. Or you make a sample which will contain weld metal, heat affected zone, as well as the base metal. But if you want to evaluate the properties of the heat affected zone itself, and we know that in the case of alloys and steels, for example, the heat affected zone is very complex, and there is different kinds of microstructure in the heat affected zone itself, and each microstructure can have different property. So if you want to characterize the properties of the heat affected zone, there is no other method, whereas this method comes, it will allow you to do that. But it is not all rosy there. There are many limitations. The first and foremost is about the mode of loading. See, most of the tests, mechanical tests that we do are tensile tests. Loading is tensile. But in these innovative tests, the loading turns out to be either compressive or bending mode. And since the tests, these are all quick tests, testing time is short. But when it comes to alloys, which can undergo microstructural changes over a period of time when exposed to high temperature, we'll be able to capture that effect in a standard test, where, for example, a creep test may go for hundreds and thousands of hours. But since these tests are short duration tests, we may not be able to capture the changes in the property of the material that occurs as a result of microstructural changes. It's a localized testing. So if you're looking at average bulk properties of the material, then it is not represented. The test is not difficult. Testing is not difficult, but interpretation of the result is pretty complex. And that is where still a lot of questions are there. What you see here is, one second. So what you see here are 3 specimens. This is a 10 millimeter diameter specimen, about 5 millimeter thickness. This is a ball indentation sample. You will find that already there are about 7 tests done. And each of these depth of this impression will be much less than 1 millimeter. And this one is the impression grip sample. It's again a 10 by 10 by 10 small block of material on which one can do a large number of impression grip tests. A small punch grip is typically 10 by 10 by half millimeter thickness, and there is a fracture grip. So one sample, one grip, but the sample size is just 0.5 millimeter thick, 10 by 10. So this is the ball indentation test sample. This is the small punch grip, and this is the impression grip. And what you see here is the standard ASTM size grip sample. This is 120 millimeter long, 10 meter gauge diameter, 50 mm gauge length, and 16 mm diameter at the shoulder ends. So now coming to a little bit in detail about the ball indentation test. The test is basically a strain control multiple. What you basically do is you have a tungsten carbide steel ball, and the ball is pushed into the material under strain control conditions. You don't push the ball in one step. You do it in multiple steps, and every step, so you will initially define what is the total depth of the penetration that you want to do. That is divided into some 6 or 7 equal amounts, and then in 6 or 7 steps you are penetrating the indenter into the material, and every time you are not penetrating the material fully inside, it's only partly inside, so there's a partial unloading that happens. So it is called a strain control multiple indentation involving partial unloading. So as the indenter penetrates the material, you measure the load, you also measure the depth of penetration. So you have two data. So your raw data is the load as well as the depth of penetration. So you have a large, you'll get, if you are doing 7, every time you are penetrating, you will generate a large amount of data because continuously you are measuring the load and depth of penetration, and that is repeated 7 times or 9 times. That can vary. So in this way, you are generating a large number of load and depth data from one experiment. So once you have this data, then you can process it, apply elasticity and plasticity theories, also certain semi-empirical relationships, and you can derive the tensile properties, hardness, as well as the fracture toughness of the material. So what you see here is, one ball indentation test. The x-axis is the depth of penetration, y-axis is the load. You see that you start here, so the depth, so this is the depth of penetration, and then partial unloading. Again, you are increasing the depth, then it is followed by unloading, then again loading. So it is done, and after about 7 steps, once you have reached the preset value of total depth of penetration, once you have reached that, the sample is unloaded. So once you process the data, what do you get? You will get monotonic true stress, true strain curves. And the assumption is, in this case, that the true stress, true strain curve, which you have generated under compression mode, compression loading, is similar to the true stress, true strain curves in tension. Another assumption in this processing of the data is that the indentation strain can be correlated with the strain in a uniaxial tensile test. And when you apply the ball, there is a pressure, and the mean ball pressure can be correlated with the stress in uniaxial tension. And another important assumption is that the stress triaxiality and the deformation energy at the tip of the indenter is similar to what exists at the tip of a crack in a standard fracture mechanics test. So you have here a ball, you are driving it into the material, you measure the depth of penetration, you measure the corresponding load, but this process is repeated multiple times, and you have the depth of penetration and load data. And From that, you are generating the stress strain curve. Now, I should mention here that when a rigid spherical ball indenter is allowed to penetrate into a metal, then the material under the indenter will be in a triaxial state of stress. So the material immediately under the indenter will be in the will be subjected to both elastic and plastic deformation. So these stresses will force the material to deform elastically as well as plastically. So this can result in an upward flow of the material, which we call pile-up of material, or it can also lead to downward flow of the material, which we call it as sinking. And here there's a lot of scope for doing finite element analysis of the material behavior under the indenter in order to evaluate stress strain behavior, stress distribution, pile-up, sinking calculations, etc., etc. So once you have this blue colored graph, which will be generated in a ball indentation test, you process this data, okay, you extrapolate it to the zero load so that you get the what is called the permanent depth of penetration. That is what I call HT. And then capital D is the diameter of the indenter. So from that, you can determine what is the total diameter of the indentation. So from the depth, we are now getting the diameter value. And from that value, we can get there's a total diameter that will be consisting of elastic and plastic. So by applying certain Hertzian equations, we can convert this total diameter into plastic diameter. And once we have the plastic diameter value, then you can determine the epsilon P, the plastic strain in uniaxial tension, using this equation. Epsilon P is equal to 1/5 dP by capital D, where dP is the plastic diameter and capital D is the diameter of the indenter. So now you have got the true strain as you would derive from a tensile test. Now you need to get the true stress. So how do we get the true stress? So again, we have the load P, which is the load on the indenter. And then you can determine the mean ball pressure using an equation like this, 4P/5 dt squared. And once you have the mean pressure, then you can evaluate the flow stress, uniaxial flow stress sigma, using this equation that sigma is equal to the mean ball pressure divided by a parameter delta. And the parameter delta is not having a fixed value. Its value will vary as the plastic zone size under the indenter evolves. So it's a bit of a complicated stuff. I'm not going into that. So the point that you may notice that we are now able to, from the load data, we are able to derive the uniaxial flow stress corresponding to each of the uniaxial flow strain value. So now that you have got the true stress and true strain value, you have many constitutive equations by which you can correlate the true stress, true strain values. Kottayam equation is a very popular one. It says that the true stress sigma T is equal to a constant K into the true plastic strain to the power of N, which is the strain hardening exponent. So this is the curve that is generated, the true stress, true strain curve that is generated from the load versus depth data that we have seen earlier. So from that curve, now we are able to generate the true stress, true strain curve. And by analyzing the true stress, true strain curve, we'll be able to get what is the UTS of the material through this relationship. UTS is equal to the strength coefficient K into epsilon U divided by whole to the power of N, where E is a constant for the materials. And applying the Mayer's law, you'll be able to determine the yield strength of the material using a relationship that yield strength is equal to beta into A. Again, the hardness also can be derived through an equation like this. So I'm not going into the derivation of these equations. All I want to tell is that from the load and depth combination data, we are able to get true stress, true strain data. From that, you are able to determine the yield stress of the material, ultimate tensile strength of the material, as well as the hardness of the material. This is the machine that we are talking about, ball indentation machine is also called the automated ball indentation machine, because most of the things, the testing part is mostly automated, as well as the analysis of the data is automated. It consists of, we have a furnace because this has a capability to carry out high temperature ball indentation tests. And of course, it has a camera also, so that you can see live what is happening inside. And this is how the ball indentation impression looks like. If you take out the sample and look under a microscope, this is how the indentation looks like. You have you will find that surrounding this indentation, you have a deformed zone. And if you look here, you can also see the localized shear bands at the indentation edge. So at IGCAR, as Dr. Reddy knows very well, we had a big research program on developing low carbon nitrogen alloy 316 stainless steel for certain important applications in fast reactors. So as part of the development of that material, we have done a lot of experiments using this ball indentation machine. So what you see here is the variation of ultimate tensile strength as a function of temperature based on the ball indentation test that we have done. So as expected, you see that the UTS decreases with increase in temperature. And these tests were carried out all the way up to 700 degrees centigrade. So that's a very strong point. I mean, this machine is able to do high temperature ball indentation test up to 700 degree, and I think the capacity is up to 800 degrees Celsius. So the experiment was carried out on a number of heats containing different nitrogen contents, other element composition, grain size, everything was kept constant, but we had multiple heats with different nitrogen contents. And this graph shows how the UTS varied with nitrogen content. As the nitrogen content in the heat material increased, the ultimate tensile strength also increased. And these findings were very similar to the data or the results that we obtained from conventional tensile tests. So another advantage of this ball indentation test is that you can make an estimate of the fracture energy of the material without carrying out the conventional or the standard CT tests. But here again, there are a few important assumptions. First is that the indentation generates a deformation field that is concentrated around the area of contact of the indenter with the sample. So, and the deforming volume of the material, it is small, but it is surrounded by a large volume of non-deforming material. So as the indenter penetrates the material immediately under the indenter undergoes deformation, elastic and plastic. But then it is constrained by a larger volume of material which is not undergoing deformation. So a degree of constraint is being exercised on the deforming material by the surrounding material. So the deforming volume of the material being small, but it's surrounded by large volume of non-deforming material. So this constraint is considered to be similar to the degree of constraint that exists at the crack tip. For a crack to progress, it depends upon the kind of triaxiality at the crack tip as well as the kind of constraint that it is facing for the propagation of the crack. So a kind of equivalence is conceived in this case. And it is assumed that the stress triaxialities at the center of the contact area, of the indenter and the material, the kind of stress triaxialities that exist, and those that exist at the crack tip are similar. And this has been proved by other researchers through finite element analysis. So then it is assumed that deformation energy at the center of the indenter and at the front of a crack are similar. If that is so, then deformation energy per unit area absorbed by the material at the root of this ball indenter up to a critical stress can be a measure of fracture toughness of the material. And that is what is called indentation energy to fracture, which would mean that if I were to continuously allow the indenter to penetrate the material to a depth that will generate a stress equal to a fracture stress of the material, then the energy that is absorbed in that process can be correlated with the energy for fracture. So fracture is assumed to occur when the maximum load equals the cleavage fracture stress. That means I'm allowing the indenter to keep penetrating under increasing load to a point where the equivalent stress becomes the fracture stress. And then I calculate what is the energy that is absorbed by the material under the indenter. And the energy that is absorbed by the indenter, by the material under the indenter, is given by this equation. And that is the indentation energy to fracture. So the indentation energy to fracture can be correlated with the, for example, the Sharpe energy. So a lot of experiments were done on CF8. CF8 is a fast version of 304 stainless steel. So ball indentation tests were done from minus 150 degrees centigrade to plus 150 degrees centigrade on this material, and the indentation energy to fracture that I described earlier was evaluated. And this shows how IEF changes as a function of temperature. You find that as the temperature comes down, there's a kind of a, constant. At higher temperature, IEF values tend to be constant. But as you decrease the temperature, it continuously decreases. And then again, it tends to be a kind of reach a constant value at temperature less than minus 100 degrees centigrade. So you would imagine that this is a kind of a ductile to brittle transition curve that you will generate in a conventional impact test. And this curve represents the data obtained from standard impact tests, CVIT, using Sharpe specimens by carrying out tests roughly in the same temperature range. So you find that the shape of the curve is similar. Yes, the values are not comparable. Like for example, here we have values in the order of 1000, 2000, etc. Whereas here we have values in the tens. So values are not comparable, but the shape is comparable, which would mean even the DBTT temperature can be determined from this graph. So just by doing ball indentation tests on a material, on one sample material, you will be able to get an estimate of the ductile to brittle transition temperature. So now this is a cross plot of these two graphs, the red and blue. Cross plot is what you see as the black one. So on the y-axis, you have the Sharpe energy determined from this graph. And on the x-axis, you have the IEF determined from this. So you find that there is an excellent correlation between the Sharpe energy and the indentation energy to fracture. So we have done a lot of finite element analysis at IGCAR to kind of support the assumptions that I have described earlier. Again, let me skip that. So to summarize, ball indentation test is a very useful test in order to evaluate the tensile properties of the material, fracture energy, and the hardness of the material. Now I will come to impression creep. So as the term itself tells us, the creep deformation is determined under compression loading. So what we do here is that at a constant load, the creep means what? The deformation that happens at a constant load at a constant temperature. The deformation as a function of time is the creep curve. So in the impression creep, again, the load is constant, temperature is constant, and what we do is, under the action of this constant load, a flat-ended cylindrical indenter, typically about 1 millimeter diameter, is pushed into this material. When the material is pushed, the depth of penetration is measured as a function of time. So although the temperature is constant, the load is constant, this indenter will continue to penetrate deeper and deeper into the material. And as it penetrates deeper and deeper into the material, you measure both the depth of penetration and the corresponding, or you measure the at fixed intervals of time, what is the depth of penetration. So if you plot the depth of penetration data as a function of time, this is what you get. So it is similar to a creep curve. So you have an initial loading strain, and then you have the transient or the primary creep, and then you have a secondary creep. But no fracture will happen in impression creep because the material is under compression loading. So there is no fracture in this case. But you get a curve which is very similar to the standard creep curve. So how do you analyze this creep curve and then generate important information that we need, which we would have got otherwise from a standard creep test? In this case, we have the load L. And so first is you calculate the mean pressure under the punch. So you have a punch, cylindrical punch of diameter small d, and you are applying a load here, capital L. So under action of the load, and so you can calculate what is called the mean pressure under the cylindrical punch. Sigma is equal to 4L divided by pi d squared, where L is the applied load, small d is the diameter of the cylindrical indenter, and P is, or sigma m, is the mean pressure. And now you can also determine what is the velocity of penetration. The velocity of the penetration is nothing but dH by dt. We have the depth of penetration data as a function of time. So dH by dt will give you the value of the impression velocity. So now you have got the mean pressure as well as the impression velocity. Now, how do we convert it into strain and stress? So the impression velocity can be related with the uniaxial stress sigma using a relationship that sigma uniaxial is equal to a constant alpha into the impression mean stress, sigma IMP. So we have sigma IMP, we have calculated as 4L by pi d squared, multiplied by a constant alpha, then you get the equivalent uniaxial stress. It turns out that alpha is around 0.3 for a large number of materials. You will see here, alloys and metals, quite a bit of them. And the value of alpha is all about 0.3. So it's a constant. You ask me why it is a constant, I have no idea, but that is the empirical evidence. So you have got the uniaxial stress. Then you have the velocity of penetration, and how can we convert it to the creep rate, strain rate? Now again here strain rate is given by the impression velocity divided by beta into d, where beta is a constant and d is the diameter of the indenter. And again, it turns out that the beta is equal to 1 for a large number of materials. So we have two constants, alpha, to convert the impression, the mean pressure into uniaxial stress. And then we have the constant beta to convert the impression velocity to strain rate under uniaxial tension. So now we have both sigma as well as epsilon dot. So obviously now we can correlate stress and strain rate and generate the various other important relationships like Norton law, etc. So this is how the impression creep data is converted to equivalent strain rate and stress data. This shows the experimental setup. Anyway, it is not necessary to go into detail. This is the furnace, the sample is inside, and it is under vacuum. And you have the loading mechanism, strain measuring, the depth of penetration mechanisms, etc., etc. So this graph gives you the results of impression creep tests on 316 Ln stainless steel at 923 Kelvin at 1, 2, 3, 4 different loads for 72 to 760 megapascal. So you see here you get typical creep curves at all the stresses, and as expected, as you increase the stress, you find that the creep curve moves up when you plot it as depth of penetration versus time. So the creep curves are characterized by a loading strain, a primary creep stage, and a secondary creep stage. As I mentioned, there will be no tertiary creep stage in impression creep because there is no necking and no fracture. And with increasing load, depth of penetration increases. So you can always, from these creep curves, you can generate while this is depth of penetration versus time, you can generate the rate of penetration as a function of time graph. And you find that, again, the rate is very high and then it becomes steady. So this is the steady state deformation. So you get a very well-defined steady state in impression creep test. What you see here are the impressions left behind at the end of the impression creep test. So one 10 by 10 by 10 sample block was used for carrying out, in this case, 5 impression creep tests. This shows the correlation between steady state impression velocity and punching stress. On a log-log plot, you find that there's a linear relationship, so which is very similar to the Norton law. And the slope is equal to 7.6, which is the so-called stress exponent. And that is the number that we expect from standard uniaxial creep test, a value of n in this range at this temperature. So the Norton power law is obeyed between steady state impression velocity and the punching stress. So the next question is, how do we correlate the impression creep data with the data from standard conventional creep tests? And I already explained you the conversion of the mean pressure to uniaxial stress and the impression velocity to strain rate with constants alpha and beta. So this is the correlation. On the y-axis, you have the steady state creep rate. I'm sorry. So this is again, a log-log plot of steady state creep rate versus stress. And the red square data points represent the uniaxial creep test from standard test, and the circles represent the impression creep test, and you find that there's a very good correlation and the slope is the same. So now you find that you are able to convert the impression creep test data into the data that you would have otherwise obtained from a standard creep test. But one thing that is missing in an impression creep test is you don't have any idea about the fracture life of the material, which is a very important property in creep test. So how do we do that? There are certain methods. One is using the very well-known Monick-Mangan relationship. This is a very well-established relationship between steady state creep rate and rupture life for a large number of materials. So this shows, so once you have the steady state creep data, you can always, using the Monick-Mangan relationship, you can derive the rupture life data. So although impression creep test does not lead to rupture, you are able to generate the rupture data. This shows, some of the finite element analysis that was carried out. So this is an EBSD micrograph. You can see here that there are 3 layers of deformation. A region 1, that is this one, where the grains appear to be somewhat equiaxed, which would lead us to assume that the material under this region, in this region, is under hydrostatic stress. That is what you see here. And then a region 2, where you will find that the grains are all deformed. They have been subjected to shear stress. So there's a lot of shear deformation happening in this region. So here you have an equiaxed grains, under that all the elongated sheared grains, and then the material under that is again equiaxed with no plastic deformation. So if we look at the material under the indenter in an impression creep test, you will find these three different patterns describing the kind of deformation that has happened. And another thing, of course, there will be the pileup of material, etc. Because as the indenter goes inside the material, it has to be accommodated either by the material surrounding the indenter, or some of it will have to be thrown out in the form of a pileup. And you can always measure that using surface profilometer and then derive a lot of information from that, both as a function of time as well as a function of stress. Yes, this is coming back to our alloy development program, where creep tests are always very long. In fact, IGCAR has the record of having conducted the longest creep test. 1,50,000. Yeah, it was 20 years, close to 20 years. One creep test was continued before it fractured. So we cannot do that kind of creep test for materials alloy development program. So we were trying to optimize the amount of nitrogen as far as the creep and fatigue properties were concerned by preparing a number of heats, laboratory heats with various amounts of nitrogen. So this data is about the optimization of the creep properties using impression creep test. So the steady state impression velocity as a function of the nitrogen content. So this shows the variation of the impression velocity as a function of, as you increase the nitrogen content from 0.06 to 0.22 at an impression load of 472 megapascal. And the other straight lines represent the data obtained by carrying out impression tests at other different loads with equivalent stress. So what you see here is as the nitrogen content increases, the steady state impression velocity decreases. So the material becomes creep stronger. And of course, as you increase the stress, the steady state impression velocity increases. So the steady state impression velocity decreased with increasing nitrogen content at all the four stress levels, and that those results are consistent with the results from uniaxial tests. And it was also observed that the impression velocity was sensitive to even small variation in nitrogen content in the steel. Because if you see here, there were 4 different nitrogen levels, and the difference between each of these was not high. I mentioned that one of the unique advantages of this impression creep test is that you are able to determine the creep properties of various microstructural zones of a weld joint. What you see here is a weld piece. You have the base metal, you have the weld metal. So this is the microstructure of the base metal, equiaxed grains. And the weld is dendritic structure with delta Freud, some 4 to 8%. And then you have the heat affected zone. That means the region immediately next to the weld metal is having a large grain size. And as you move away from the heat affected zone, the grain size decreases. So using the impression creep machine, we carried out creep tests, the base metal, heat affected zone, and the weld metal. This shows the creep curves of the 3 different microstructural regions. The top one is that of the weld metal, the middle one, the red one, is the base metal, and then this is the heat affected zone. So it turns out that the 316 Ln stainless steel welds, the weld metal is the weakest, and the heat affected zone is the strongest. But if you do similar tests in a ferritic steel, you will find that the heat affected zone is the weakest. Yeah, this is the same data. You process it to obtain the rate. So impression velocity as a function of time. So the creep rate is lowest in the heat affected zone and highest for the weld metal. And the impression velocity decreases with time. Now I move on to the third one. I know I am running out of time. That is small punch creep. This is a block of 120 by 20 by 20. Out of that, I can prepare one conventional creep test specimen meeting ASTM standard. But when I am talking of small punch creep test, I'll be able to generate 800 samples from this single block, because the size of a small punch creep is only 10 by 10 which is the same as this cross. This cross section is 20 by 20. Yeah, I need only 10 by 10, and the thickness of the specimen is just 0.5 mm. So just one block of specimen of 120 by 20 by 20 can generate 800 small punch creep samples. So that is why I say it is material non-intensive. So some of the basics aspects of the small punch creep is, yes, the sample size is very small. Then what is the indenter here? The indenter is a silicon nitride spherical ball, around 2 to 3 millimeter in diameter. And you load the specimen with this 10 by 10 by 0.5 mm square specimen using this indenter. So the spherical ball is loaded, the ball is touching the sample. So as the ball is loaded, and once the ball is loaded, the specimen undergoes creep deformation. The specimen is loaded by the ball at a constant load. And of course it is creep, so temperature is high. And the test continues till it is sample breaks, the material rupture. So obviously here it is not compression mode of deformation, but what happens to the sample is it is undergoing bending deflection. So instead of measuring depth of penetration in the case of impression creep, in the case of small punch creep, you are going to measure the bending deflection as a function of time. So this is the sample. This is your ball, the ceramic ball, and you have the ram here. With the ram, you are loading the ball, and once the ball is loaded, it is loading the sample also. So a constant load L is applied to the specimen through the spherical ball, and the bending displacement that occurs is recorded as a function of time. So once you have the time data and the deflection data, you can make a plot of deflection versus time, and that is what is called the small punch creep curve. And the small punch creep curve, though it is a measure of deflection versus time, it will have the imprints of primary creep, secondary creep, and tertiary creep, just as you get it in a standard creep test. So in the case of small punch creep, it is bending that is happening. There is both elastic bending and plastic bending and membrane stretching. So when the punch initially contacts the disc specimen, what happens is elastic bending. Slowly the yielding happens in the highest stressed region. That is the region at the root of the spherical ball. So that leads to plastic bending, and the plastic bending region expands. So the yield front expands through the thickness of the specimen and radially outwards. And the next stage is membrane stretching. That is when the yield front extends beyond the region of contact between the punch and the disc. And that region will be under a biaxial stress state. So this process continues with time, and finally there will be necking, and necking will result in failure. So when this bending happens in the bending region, there will be a rapid increase in the contact area with an increase in the central deflection. And the contact area is controlled by the bending deformation. But in the case of membrane stretching, it should be noted that the contact area is controlled by the reduction in thickness. This is the small punch creep machine. Again, let me not go through it. All the three machines that I have shown you are taken from IGCAR. These systems have been there for many years, and they have produced with these machines a lot of valuable data has been generated. So this is a typical SPC curve, deflection versus time. The test has gone close to 1000 hours. You have the typical shape, you have the loading strain in the primary, secondary, and tertiary leading to rupture. And you get the deflection rate versus time curve as expected. As I mentioned, bending is the dominant mode of deformation in the primary region. Membrane stretching is the dominant deformation mode in secondary and tertiary regions, and rapid increase in tertiary due to localization of deformation and crack formation. leads to fracture. So from a small punch creep test, you are able to determine the deflection rate and also the minimum deflection rate. You can determine the rupture time and what is the total deflection at rupture. This is how the sample will look like once the rupture has occurred. This graph is nothing but variation of SPC curve with the load. So each graph is a variation of deflection rate. Sorry. Each curve is a variation of deflection rate with time, and different curves represent different loads. So as you increase the load, you find that the deflection rate increases, but the shape of the curve is similar. That means the rate decreases, which is a constant value, and then it increases. So if you plot the deflection rate as a function of 1 second. If you plot the deflection rate as a function of stress, you find that on a log-log plot, you get this standard tensile straight line curve, which is nothing but the expression of Norton's creep law with a slope of 6. So this is the data generated from the SPC curve. So all the data at different stresses, the minimum creep rates or the minimum deflection rates have been plotted as a function of stress, and you get a linear relationship, which means it obeys a Norton power law. Now, how do we correlate the small punch creep data with conventional creep data? So this graph shows how the variation of, see, this is the data from uniaxial test, stress versus rupture life. And this is the data from the bending test. Again, rupture life versus, so here it is load versus life, and here it is stress versus life in the uniaxial data. Now we have to find out some correlation between uniaxial load as well as the SPC load. So this is the kind of relationship that has been generated between the F, that is the SPC load, and sigma, the uniaxial stress. So F by sigma is equal to K into R into T squared by H into D. So capital F is nothing but the SPC creep load, and sigma is the uniaxial stress that is found to be equal to some constant K into capital R, which is the radius of the punch indenter, into T, which is the thickness of the specimen, then H, which is the radius of the receiving hole of the indenter fixture, and capital D is the ductility factor for the material. So it's a complex relationship, but it's like an empirical relationship, and this has been found to be useful for correlating the SPC data with uniaxial rupture data. Yeah. So once you use this formula, this equation conversion relationship, and convert the data, you will get an excellent correlation between SPC test and uniaxial creep test in terms of the rupture life of the material. Again, this F by sigma, it turns out to be about 1.75 for most materials. So you will find that out of all the three innovative methods of testing that have been discussed so far, there are a lot of empirical relationships. And what is the physical basis for those relationships? A lot of work needs to be done. But it is good that many times these numbers are constant and they are valid for different materials, different experimental conditions, etc., etc. So from SPC creep test, we have determined the rupture life and how with different nitrogen contents, the rupture life varied. You find that again as expected. Sorry. As you increase the rupture life, as you increase the nitrogen content, rupture life increases. So increase in nitrogen content increases the rupture life, just as the observations obtained from uniaxial creep test. So we have been able to obtain excellent correlation between the results from these kinds of innovative tests versus the data obtained from conventional tests, but it involves a lot of assumptions as well as empirical relationships. So to summarize, ball indentation creep, and small punch creep are innovative testing techniques that are suitable for evaluation of tensile, fracture, and creep properties of materials. A large amount of data can be collected from one sample, and that not only reduces the effort for sample preparation, but it also reduces the sample-to-sample variation in properties. So it's a very useful tool for assessment of structural integrity of materials, because you want to assess the properties without compromising the structural integrity of a component or an equipment. So it has to be material non-intensive. You cannot remove large parts of the component to do the evaluation. So from that point of view, it's considered to be material non-intensive and suitable for assessment of structural integrity. It's very useful for other development programs, as I have demonstrated that rapid screening of mechanical properties of multiple laboratory heats for optimizing the composition can be carried out in short time. And weld joints can be characterized. Different microstructural zones in the weld joint the properties can be characterized. And it is nearly non-destructive. You will find the ball indentation leaves a small spherical indentation. Likewise, in the case of small punch creep also, in the case of impression creep also. But the small punch creep, of course, it is destructive because samples breaks. But you don't need a lot of material to do this test. So to that extent, you can say that your the structure is kept intact. I must also point out the limitations which I have been listing out one after another during the course of this presentation. One is that since the test time is generally short, often much less than 1000 hours, the creep behavior due to long-term microstructural changes cannot be captured. Secondly, rupture life cannot be determined by the impression creep technique because there is no fracture occurring. The type of loading is compressive in ball indentation and impression creep, and predominantly bending in the case of small punch creep. Unlike conventional creep tests which are carried out, or conventional tensile tests which are carried out under tensile loading conditions. Again, it is not monotonic loading, uniaxial loading. Here it is complex and multi-axial. And the kind of deformation that material undergoes is heterogeneous, because the amount of material under the indenter is undergoing elastic, plastic, and creep deformation and is subjected to a lot of constraints. These methods have to use a lot of empirical correlations to generate the equivalent data under uniaxial conditions. But most of them have been validated through finite element analysis, but a lot of work remains to be done. So to end, I would like to thank my IGCAR colleagues, where most of these experiments were carried out, where we have been able to establish these state-of-the-art facilities. And I'm glad to hear from Dr. Varaprasad Reddy that these machines are still generating tons of data, very valuable information. And I should also thank my mentors, Professor K.L. Murthy and North Carolina State University, from whom I learned a lot about ball indentation. From Professor Komasaki of Kagoshima University in Japan, from whom I learned about small punch creep, and my interactions with Dr. J.C.M. Lee and Dr. Professor D.H. Shastri on impression creep. So that brings me to the end of my presentation. Thank you all for your kind attention.
Thank you, sir. Thank you very much for the nice and very informative presentation. And we have covered the advantages and limitations of material intensive tests, and you have covered in detail three different methods: ball indentation, impression creep, and small punch test. With the details of the test and also results of these studies, comparing with the results of the conventional tests, as well as the results of experimental as well as numerical studies carried out using finite element analysis. Now we'll open the presentation for questions. Let me check if there are any questions in chat.
I had one. Maybe I could just start off.
Yeah, please, sir, please.
In this small punch creep test, you mentioned that there's a phase in which you have basically membrane stretching. Can you hear me?
Yeah, I can hear you. I'm here.
Oh, okay.
I'm here. Yes.
So in that membrane stretching period, is most of the deformation accommodated by the stretching, or there is also the bending going on beneath the ball?
Right. Yeah, actually there is membrane stretching undergoing. Happening under the ball till fracture.
I see. So when there is stretching, that the thickness of that sheet is under sort of a biaxial tension, is it?
Yes.
Because in bending you'll have
yes,
opposite stresses,
right.
compression and tension.
You are right. It will be under biaxial stress state.
I see.
So that is why,
Thank you.
see, in a standard conventional creep test, you have a big volume of material, monotonic loading, uniaxial, entire material sees the same stress, and material uniformly deforms till it enters the tertiary stage. But in all these tests that I have described, is quite complex. It keeps changing as the test progresses. But the beauty is at the end of it, you are able to correlate the data with conventional tests with a lot of magic.
Thank you.
I think Sundar sir has a question. Sir?
Yes, please.
Yeah. Dr. Mathew,
Yep.
You said that you are in administration right now. So I have a question of administrative nature, and that is with the promising correlation between the three methods that you described in a very lucid fashion. Thank you very much for the lecture. It was very informative. Between the results that are obtained and the correlation with the conventional test results, what is the the process in the regulatory sphere, in life extension for nuclear power reactors, in certification of design, in certification to start operating equipment, power reactors and so on. What is the extent of acceptability of test results obtained from these indirect methods, if you can call them?
Very good question. See, as far as I know, in the case of ball indentation, as well as a small punch creep, a lot of work is going on to get these things in the codes. Like we have code for conducting uniaxial tests for be it creep, fatigue, tension. Likewise, to bring out codes for small punch creep and ball indentation, work is going on as far as I know, but not as I don't know any work in the field of impression creep. And this data is being used extensively in other countries for structural integrity assessment, because you have a large database of the virgin material, and once you have these correlations established, then at any point of time you can go to a component into the plant and then extract a small bit of this sample and then prepare it and then do the test and try to correlate. And ball indentation machine is available field version also. You don't have to necessarily extract the sample or material. You can go to the field on a pipe, oil rig or bridge or whatever it is. Commercial equipments are available, and you can go there with this machine, the field machine, and then do the test there and generate the data with respect to tensile and fracture energy, etc. And they are being used for structural integrity assessment. Now, back in the nuclear system in India, I am not aware of these things being used. See, we have at IGCAR we have these facilities and we have done a lot of studies, but not in any other. In BRC, they have done some ball indentation tests because this is very useful for doing tests on irradiated material, but not small punch grip and impression grip. So very limited amount of studies have been carried out in India, and therefore, not that I know of where in the nuclear domain these tests are being used for structural integrity assessment. But in other countries, yes. In fact, the ball indentation machine, the pioneers were from Oak Ridge National Lab, and they have used it for nuclear in the nuclear installations.
El Haddad.
Fahmy Hagag also. So does that answer your question?
Yeah, it was a very diplomatic answer, but anyway, thank you very much. I can understand because you are not part of the system anymore, so probably you may not be aware of the paperwork that's been going on. My interest comes from life extension programs, because when you have aging power reactors and the question arises about whether to retire them, these methods that you described are so powerful in almost being non-destructive.
Yes, they're very powerful, but the point is, I would say, you need to do, a lot of research more and remove the ambiguities where you have a kind of lot of these correlations, empirical correlations have to be taken off and substituted by fundamental understanding, especially the deformation analysis of the material, and generate large database also. And acceptability will come once it enters the code. Till it enters the codes, no, acceptability will be always, especially when it comes to these regulators for life extension and all. They'll be very careful.
Right. Mm-hmm. Thank you.
So may I add one point, sir, here? Mathew, sir?
Please.
This is Reddy, sir, Prasad Reddy. In fact, recently this ORNL has now started one round-robin testing program on translating this data from SPT and ABA to a standard. They're working out an ASM standard and working with IGCAR also from Irradiation Lab. Dr. Karthik was a part of that. And from ORNL, Michael Sokolo was a part of this round-robin testing program. They're planning to bring this because what is happening is now for remaining life assessment, they are keeping very small coupons in the reactor at grid plates and near the clad tubes, inside the clad tubes. So over a period of time, after the irradiation, they're taking those coupons. Since they're being only very small 5 diameter capsules, they're able to use only these techniques. Now, once they standardize the techniques with the base metal data, they are now utilizing the same correlations and the empirical factors, whatever they established for the irradiated specimens also. In that way, they are able to judge the kind of dose that material has seen in the reactor. This is one of the programs they have recently initiated, sir.
Very good. Yeah, that's news for me. And definitely, it has a lot of potential. See, in earlier days, what they were, due to irradiation, the main problem is material becomes brittle. So you need to know the fracture by the impact energy. So earlier days, they used to keep a lot of impact samples, but subsize samples. Of course, then the question is, how do you correlate the RP energy from a subsize sample to a full size sample? But since the volume of available volume for keeping these samples inside a reactor is limited, they used to keep subsize sample and used to withdraw the sample, at various intervals of years. That is basically fluence, and then take it out, do this test, and continue to monitor the reduction in the fracture energy or sharp impact energy. That is what they used to do. But then, as I said, the volume of material that you can keep inside the reactor is limited. And now this is here you need only miniature sample. So I think it's a good decision that they are replacing those big samples with these smaller miniature samples.
Good evening, sir. This is
Professor
Atul from Akua.
As I said, I am in a different loop now, so I am not having access to the latest information like what Dr. Reddy shared now.
Hello, sir. This is Atul Balal from Nagpur.
Yes, sir. Your voice is same when I used to talk with you about again more than 10 years. Yes.
Right. Always nice to listen to you. So it was
I have
again
learned a lot of things from you.
Sir. Sir, I just wanted to check, like, say, how uniaxial compression creep correlates with these data. Like, we can have uniaxial tensile conventional. How about like uniaxial compressive creep, where sample requirement will be in a disk shape?
Yeah, if I had to give a non-technical answer, seeing is believing. You have seen the creep curves from impression creep. You have seen the creep curves from conventional. You have seen in a creep test, the important parameters are the steady state creep as well as the rupture life. So we have seen that there's a very good correlation, no? So I tend to argue like this, that okay, as far as the deformation is concerned, see this in impression creep, you are not moving into rupture. So rupture is associated in a creep, the rupture is associated with the generation of defects. I mean cracks and cavities at the grain boundaries, leading to the cracks joining and then microstructural degradation over a very long time, etc., etc. So till such point of time, it is only about deformation. And what is the creep deformation? It's either diffusion creep or it is dislocation creep. And under conditions where we do laboratory experiments, it is dislocation creep. So dislocations, I think they will move in the direction of the stress, no matter whether it is left or right.
Right, sir. So this is basically coming from, say, nowadays with material scarcity, the people are asking about, like, can we do with miniature specimens, but not with the thickness of 0.5 mm as in SPC or something.
Correct.
So in that sense, like, if we can use compression creep, so then again mechanisms have to be studied in a different line, maybe.
Correct. Let me add 2 points. One is, see, even when we do a hardness test, there is a relationship between, depending upon the diameter of the intender and the thickness. If you are using a large diameter, your material has to be thicker, right? I think there's a ratio of some 1:3 or something. That is, your depth the sample thickness should be more than 3 times the depth. So likewise, so in this case, you can have small sample, but then depending upon how much you want to penetrate. The second point I wanted to mention is, among these three equipments, ball indentation, small punch creep, and impression creep. If you look at the cost of the equipment, impression creep is much less than small punch creep equipment.
Yes.
And less complicated. Only thing, you cannot get rupture data, but then you can always, if you believe in the Monic-Mankind relationship, then as long as you have the the steady state creep rate, you can generate the rupture life. You can evaluate we can derive the rupture life.
Right, sir. Thank you.
Thank you, sir.
Dr. Prasad, you have any questions? Prasad Reddy?
Yes, sir. Sir Mathew, just one small guidance we need. For example, suppose if we have an unknown material, because for which we don't have these correlation coefficients, so in such cases, how should we proceed actually? Is there any, of course, we have to do a uniaxial test and then correlate, but there are some standard constants, like maybe mission dependent constants or some other constants, whether that needs to be generated in some other way or
yeah, in the case of ball indentation test, both the alpha and beta are roughly the same for all kinds of materials. So there you have no issue.
For unknown material.
Yeah, you can use the same numbers, because for a lot of materials, it has been shown that the number is the same.
Yes, sir. Yes, sir.
In the case of small punch creep, again, you have a value which is roughly 1.75. That is the ratio of that load and the load to uniaxial stress is in that range. But you will have to generate, at least you will have to do a few experiments and generate this number, and then of course you can use it.
Okay. So there are, when we extract this data from the machine, we don't, there may be some machine dependent constants also will come into picture sometime?
No. See, the machine dependency is not there. See, what are the experimental variables? It is only load, or the stress.
Yes.
And temperature, which are the same, whether you are doing it in uniaxial or in these kinds of tests. So I don't think, but as I said, all these are constants, so these are magic numbers, but we have to really, make better sense of those things by doing. And I believe that, a lot of FEM analysis can be done and one can get really deep insights into what is happening under the ball or in a ball indentation or under the indentation in an impression creep, or how the bending, the conflict between the elastic, plastic and membrane stretching is happening in a small punch creep. A lot of things can be done and analyzed.
Okay.
But as I despite this weakness of having all this empirical correlation, it works. It has been found to work fairly well.
Okay. Thank you, sir. Thank you.
Most welcome.
Any other questions?
For me, anyway, it is like, having some enriched oxygen today. Because I've been able to discuss my old subjects with experts like you. And then it's really great.
Professor, there are no other questions. Can we end the webinar?
Yeah. Thank you.
Yeah.
Thank you very much, Dr. Mathew. It's a very interesting talk. Very illuminating.
And any one of you, if you are planning to come to the central part of Kerala, please let me know, and I would like to meet personally and translate this virtual meeting into physical meeting.
Okay, thank you.
And on behalf of InSIS, we would like to thank Dr. Mathew for taking his time and for giving the presentation and also for interactive session. Thank you, sir. Thank you. We are on time. We are closing by 7:30. Thank you very much, sir. Thank you.
Thank you.
So, Dr. Sundar, you are still in Bangalore base or global base?
No, I'm right now in Moscow, in Russia.
Oh, so my guess was right.